Hello, my name is Katelyn Oh, and today I'll be talking about geometry that particularly pertains to the AMC 8 and 10. Specifically, I'll be going over the use of similar triangles and also the use of angles when approaching geometry problems. So, similar triangles. Similar triangles are triangles that have congruent corresponding angles and proportional corresponding sides. From the diagram, we can see that the angles in the first of the two similar triangles are equal to the corresponding angles in the second, and we can also derive the following ratio from the proportionality. We can use the following methods to figure out whether two triangles are similar. If two corresponding angles are equal, the triangles are similar by the AA similarity postulate. If three corresponding sides are in the same ratio, the triangles are similar by the SSS similarity postulate. And finally, if the ratio of two pairs of corresponding sides are equal and their included angles are also equal, the triangles are similar by the SAS similarity postulate. Now that we have covered the basics of similar triangles, I'll move on to some examples commonly present in competitive geometry problems. If you can spot a pair of parallel lines in a triangle, it is likely that there is some form of similarity involved. Here are two basic diagrams of what this could look like. When two parallel lines are cut by a transversal, the resulting alternate interior angles are congruent. Therefore, with this theorem established, angles B and D and angles C and E are congruent to each other. Thus, triangle A and B in both diagrams are similar by the AA postulate. Similarly, this diagram shows three pairs of similar triangles in a single large right triangle, and this also exhibits and establishes the AA postulate. Now, here are some examples from the AMC. I'll give you a moment to read the question. So let's begin by labeling the diagram. We'll call the triangle ABC, where AB equals 16 and AC equals BC. D is the midpoint of AB, and E is the point where AC is tangent to the semicircle. Using the Pythagorean theorem, we can see that the congruent triangles ACD and BCD are both 8 by 15 by 17 right triangles. Now, applying the concepts we previously covered, we can see that AED is similar to ADC by AA similarity, with angle EAC congruent to DAC and angle CDA congruent to DEA. We can thus establish the following proportion and solve for DE. Multiplying both sides by 15, we find that DE, the radius, is equal to 120 over 17, and thus the answer. Moving on, this is another question from the AMC 8. I'll give you a moment to read the question. First, notice that ABF is similar to CEF by AA. Given that E is the midpoint of side CD and thus that EC is 1/2, we can set up the ratios AB to EC is equal to 1 to 1/2 and BF to FE is equal to also 1 to 1/2. That being the case, the area ratio of triangles EFC and BFC would be 1 over 4. Since the area of triangle EBC is a quarter of the square, applying the 1 over 4 area ratio, we can see that triangle EFC is 1/12 of square ABCD. Now, because we were given that quadrilateral AFED is 45, we can use the mentioned ratio to find that 45 is equivalent to 5/12 of the square. Solving for the area of ABCD, we can thus conclude that the answer is 108. Moving on, this is a question from the 2018 AMC 10A. Once again, I'll give you a moment to read the question. Let the center of the surrounding circle be O, and let the circles that are tangent at point A and B have centers C and D respectively. Connecting A, B, C, D, AO, and BO, we can see that triangle OCD is similar to triangle OAB by AA because CD and AB are parallel. Using this similarity, we can write out the ratio OC over OA is equal to CD over AB. And solving for AB, we can conclude that the length of AB is 65 over 4, making the answer 69. Now I'll move on to the next topic, angles. And first, I'll be dealing with the sum of interior angles of polygons. It is important to note that this sum is always a constant value, regardless of whether the polygon is regular or not. That being said, the sum is given by the formula 180 multiplied by the number of sides minus 2. Here are some examples. As known through the triangle sum theorem, the sum of a triangle's interior angles is 180, which evidently we can also derive using this method. Same goes for any pentagon. Adding up any 5-sided polygon's interior angles, we will always get 540. Now, this example comes from the 2016 AMC 8. A few moments to read the question again. Connecting the points, we can see that triangle ABE is equilateral. Since the measure of angle ABE is thus 60 degrees and CD is a straight line, we can conclude that the measure of angle EBD is 180 subtract 60, which is 120 degrees. Since BE and BG are radii of the same circle, triangle BED is isosceles, meaning that the measures of angles BED and BDE are both 30 degrees. Because the same pertains to the AEC counterpart, we can find the measure of CED by adding up 30, 60, and 30, which gives us the answer 120 degrees. Finally, I'll be talking about circle theorems, which are extremely useful when it comes to competitive geometry. I'll briefly go over the 8 theorems. Number 1. Inscribed angles subtended by the same arc are equal. Number 2. Inscribed angles are half of the central angle subtended by the same arc. Number 3. Opposite angles in a cyclic quadrilateral are supplementary. Number 4. Inscribed angles containing the diameter are 90 degrees. Number 5. Angles between tangents and radii are 90 degrees. Number 6. Perpendiculars from the center of a circle to a chord bisect. Number 7. Angles between tangents and chords are equal to the angles in the alternate segment. Number 8. Tangents from a common point to a circle are equal in length. And the final practice problem, a few seconds to read. Since angles AEB and ABE are in the ratio 4:5, we can let angle AEB be 4x and ABE be 5x. Because an inscribed angle containing the diameter is always 90 degrees, using the triangle sum theorem, 4x plus 5x plus 90 is equal to 180, which makes x 10 and the measure of ABE 50 degrees. Also, angles ABE and BED are congruent because they are alternate interior angles where AB is parallel to ED. And because opposite angles in a cyclic quadrilateral are supplementary, the measure of angle BED plus BCD is 180 degrees. Finally, using substitution, we can conclude that the degree measure of angle BCD is 130, and thus the answer. And that wraps up my presentation today. Hope you enjoyed. Thank you.